Welcome everyone. Today we're going to be looking at the notes entitled Exponential Functions and the Number e. So just kind of a culminating piece on dealing with exponential functions that model y equals a times b to the x, and then introducing a new number here that'll show up quite a bit when we continue our discussions on exponential models. So let's start it out. I have a little investigation that's come up over the years. Students always ask about that b value. We've always talked about exponential growth, that b value has to be greater than 1. Exponential decay, we know that b value has to be in between 0 and 1. Well, what about a b value being negative? How does that work in a continuous exponential function? So let's just take a very brief peek at this, and then we can derive some type of conclusion from it. So here's what I was thinking we would do. Just kind of looking at a table here, looks like I'm going to have to go horizontal based on the way I presented this notes worksheet. So I'm just going to throw in some values here, and what we'll do is basically throw those inputs into the function, talk about the outputs. If we were to graph all those outputs and plot them and create a scatter plot, would it be part of an exponential curve? So let's go ahead and just start some out here, just your typical numbers. Let's do 0, a couple positives. I have a couple fractions on my sheet. We can talk about those, even a couple of negatives, just something like that, just kind of getting a feel for those being the inputs. What would the outputs look like? And so I'm going to fill this in, and you guys can do the same on yours. 2 to the 0, of course, everybody is 1. 2 to the first is 2. 2 to the second is 4. And 2 to the third is 8. So those numbers fit very nicely in. Couple good ones right here, a couple fractional exponents that we would do, 2 to the 1/2, 2 to the 1/3. So remember what that would look like, of course. This would be square root of 2, by the way. Anything to the 1/2 power is a square root. Anything to the 1/3 power would be cube root, excuse me. So cube root of 2, something like that. If we plotted those on the coordinate plane just to kind of get it out there, they would also fit in terms of our pattern. Those numbers, this would be in about 1.41. This would be in the 1.2 range. So they would definitely fit in that context and on that exponential curve. We've seen this before, of course, also. Negative exponents, that would be this right here. That would be this. And again, if we plotted all these points, and you can do this if you'd like, I don't think it's a necessity, but if we plotted all those points, we would see that they really all fit nicely on a continuous exponential growth curve. Great. B can be positive. Now, if we come over here and we look at pretty much the same situation, what tends to happen when we do a negative 2? Raised to those powers. So not the opposite of 2 to the x, but literally what if that base is negative 2? And so I'm going to do the same thing and just take a look at would it fit on some type of coherent pattern here. It looks like I'll probably just stop here as a matter of fact, just because I think we can draw the conclusion. So first and foremost, I see negative 2 to the 0 should be 1. Negative 2 to the first is going to be negative 2. Negative 2 to the second is going to be positive 4. Negative 2 to the third is going to be negative 8. And you can see already, just as I go left to right on my table here, from 0 to 1 to 2 to 3, my values are actually fluctuating. I've got a positive 1, then down to negative 2, then up to positive 4, then down to negative 8. And so you can see it really doesn't make sense with a continuous curve here. There's nothing that's going to fit that magically as an exponential growth or decay curve. In fact, when I get to this one right here, just kind of thinking out loud with it, negative 2 to the 1/2, that means the square root of negative 2, which is undefined in the real number system. So I end up getting this value that doesn't even work. This would work, but it's like the cube root of negative 2. You've got a whole bunch of things going on here. Now here's what's kind of interesting about this. Later on this year, we will actually see a context for this value right here, everybody, being negative. But that does not make sense with a continuous exponential growth or decay function. And so that's what I'm going to write right up here. So B can't be negative in a continuous, and that's the key word I think for this, exponential function. I hope that makes sense just in terms of the exponential growth, b is bigger than 1. Exponential decay, b has to be in between 0 and 1. It wouldn't make sense, obviously, guys, to have a negative number here. Again, we will see a topic that has that in place, but that'll have to wait, and we'll get to that in good time. All right, well, let's continue on here, and we're going to need a calculator for this piece. So what we're going to take a look at is one of what are called the transcendental numbers here, and it's a number that shows up quite a bit dealing with exponential functions. Again, we will see applications for this. We will see a context for it, where it fits in. For right now and for today's lesson, it's just getting comfortable with this new number and then seeing it slightly in place for a few of the exponential models. So here's what I have. It says the number e. And it says evaluate the expression, and here's what we're going to take a look at over the next couple minutes. So this expression right here, 1 plus 1 over n raised to the n for each n value, and you're going to go to 9 decimal places, which happens to be the limit on your calculator when appropriate. So I'm going to show you how to type a couple of these in. I'm going to do a couple with you, and then I'm going to ask you to pause the video and do a few of the others. And then let's see if we can get some type of pattern with that. So here's what you're going to basically type in. I'm going to go to my calculator and just go to the calculation aspect of it, and I'm just going to start typing in. So left parenthesis, everybody, 1 plus, and then 1 divided by. And notice what we're going to do here, everyone. Take a look at your n values. We're going to start at 1, and then they're going to get larger, to 100, to 10,000, to 1,000,000, to 100 million. Theoretically, everyone, I could keep going and going and going with these, but I will kind of cut it off here. I won't overplay it too much. So let's do this. In this case, our n value will be 1. So 1 divided by 1 over 1 raised to the first. And we get an answer, and of course that's going to be 2. So in this case, everybody, let's go ahead and throw a 2 right in place right there. So when n is 1, the value of the expression, the output is 2. All right, perfect. Now let's go to the next one there when n is 100. And so here we go, 1 plus 1 divided by 100. So that number is getting smaller, of course, inside the parentheses. But then I'm going to raise it to a larger number all the way to the 100th. And I end up getting this right here. So it jumped up a little bit. And so we're going to write that on our paper. So notice again, I'm going to include all the decimals, and you'll definitely see why as you do a few of these on your own. But basically, I should see something like 2.704813829. Okay, so again, when n is 100, that is the value of the expression. Now what I'm going to ask you to do is pause the video for a moment or two, and please come up with the last 3. As I said, I probably could have done quite a bit more of these, but I knew you wouldn't want to type in too many. I think we can see the pattern regardless here. Okay, so everyone pause and come on back in just a moment after you've done the last 3. Okay, when I did this, when n was 10,000, so that would be 1 plus, here we go up here, 1 plus 1 divided by 10,000 over raised to the 10,000, I should say. I get something like this. Now it's 2.718145927. That would be the value of the expression right there when n is 1,000. Now when we go from 10,000 up to 1,000,000, so changing that by a pretty large factor there, when it's 1,000,000, I end up getting this, 718, let's see, 280469, just kind of confirm that. So that would be when n is 1,000,000. So notice, major differences. Here the difference is only about 99, 1 to 100 here. Here the difference, we're going from 100 all the way to 10,000. Here from 10,000 to 1,000,000. Now look at this jump. We're going all the way from 1,000,000 to 100 million. A huge, huge leap. And what I guess I would ask you is, does it have a major impact on the value of the expression? Even though n is getting significantly larger, does it have a major impact? And you would see if you typed in 100 million as your n value, you end up getting 2.718281815. And so think about that for a second. We went up by 99 million in terms of our inputs. So an increase of 99 million. And if you look at our output here, you have to go back, let's see, 1, 2, 3, 4, 5. You have to go back 6 decimal places just to see the change. I mean, that's incredible. So you can start to really get a sense of what's going on here. Even if n is going to get larger and larger and larger, does it really have a dramatic impact on our answers? And of course, the answer to that would be no. So it says on your paper, is there a limit to your answers, or are your answers increasing without bound? And I guess I would answer that, of course, is there is a limit. Those numbers are plateauing. They seem like they are approaching something. These are not going to infinity. What they're doing is they are approaching a particular value. So let's write it as there is a limit to our answers. Okay, that looks great. And I'm going to go to my next page here, and you guys can kind of see where this is headed. And so here's kind of the idea. Here's what we're going to basically look at. So it says as n gets infinitely large, and again, you could see I was already up to 100 million. I could have gone further if I really wanted to. But as n gets infinitely large, the values of this expression approach the number e, and that's the key. They approach the number e. They're going to get closer and closer and closer. And so here's basically one definition of e. This is probably the most prevalent definition of e, and I'm going to box this up on the board here. But you can see that e is the limit as n approaches infinity. So again, as n is getting larger and larger and larger, of this expression right here. So this means limit, this lim. So it's the limit as n goes to infinity of this expression right here. And so if you kind of think about it, can I actually plug infinity into this expression and have it mean anything to us? No. But what I can do is see larger and larger and larger numbers and see that they are approaching a particular value, and they are approaching that number e. And so as you can kind of hopefully see, e is definitely going to be an irrational number. E is very much like pi. It is a number numerically that just, it goes on forever and ever and ever. There's no repetition. There's no termination on it, of course. So it says evaluate e on your calculator to 9 decimal places. And so let's go ahead and take a look at that together, everyone. There are a couple ways to do this. I'm going to show you one button on the calculator, which we probably will be using most often here. So let's kind of get comfortable with that piece. So everyone hit the second button, if you would. And then go down to where it says ln. So this would be right in here. And you can see it has this e raised to part to it. Now, of course, if we just want e, we're going to raise it to the first momentarily. But what you're going to see is e is going to be a base that we're going to be using quite a bit in exponential functions. The calculator knows this, so it already prompts you for the fact that you're going to want to raise it to a particular power. That's going to be the context for e, as a base to a power. And so let's go ahead and do this here, just e raised to the first. And again, your calculator obviously is rounding this number to, let's see, 2, 4, 6, 8, 9 decimal places. But you can see it's that 2.7, 1828, 1828. So let's go ahead and put that in. 2.7, 1828, 1828. Now again, I know that I had said that it is an irrational number, meaning it's not going to terminate and it's not going to repeat. And I know you see this repetition right here, but after this, it does not repeat. There's not another 1828 or something like that. So it's not a repeating decimal. Good. Actually, in our hallway, if you ever get a chance to take a look, we have E posted at the top of one of the walls there, and you can see it kind of going around and around. And then there's probably a little dot, dot, dot at the end of it after it runs out of room. So you can kind of check that out when you get an opportunity. And you can see, by the way, just in terms of this number right here, E, does that seem like it's just a little bigger than some of our values right here? Take a look. 2.718281815. So this is a little smaller. If I was putting in larger and larger numbers in for that expression, I would see this come up a little bit here, but it would not get bigger than what you just saw on the calculator for E. So your calculator is rounding E to 9 decimal places there. Okay, excellent. Let's see, I think I'm going to go over here and go to my next page. And let's just try some examples with it. As I said, it's a nice straightforward lesson today. We will see, again, plenty of context for using E and plenty of application for using E. For right now, it's just getting comfortable with the calculator, just getting comfortable with the idea. So let's start it out. As I had alluded to, and actually it's written here in bold on your paper, E is widely used as a base for exponential growth and decay functions. Actually, every exponential function can be written in this uniform base. Every exponential function can be written in base E. And so you see just the most basic one out there. So this would be just y equals e to the x. And so we're just going to sketch it out. What I'd ask us to do is sketch it out even without the graphing calculator, thinking about what it might look like. And then maybe we can use the calculator just as confirmation. So I guess here's the best question right away. Just looking at that piece right there, if I use base E in an exponential model, is it growth or is it decay? So think about that for a sec. And I guess you'd have to choose one or the other here. And again, remember this. If this is your rate, well, if it's bigger than 1, it's growth. If it's between 0 and 1, it's decay. And as a matter of fact, of course, what we just found is it's in between 2 and 3, and so it's exponential growth. So I think that's the one we want. And so you don't have to overplay this too much here. Again, I don't want point plotting or anything like that. Just want to get comfortable with the fact that your basic base E exponential model is growth. And let's go ahead and maybe see that in action here. You could just take a look at this on my calculator. You don't have to type it in if you don't want. But basically, I would go to my y equals and type in, again, there it is down there, e to the x, and kind of zoom standard. And there it is. Again, not perfect on my window, but you see it's definitely exponential growth. Here's a good question, just as I'm thinking about it. How would that compare to the doubling model, just 2 to the x? Well, I think you would say it's probably a little steeper. Again, I'm not sure how it'll play out in our graphing calculator here, but E is a number bigger than 2, so let's take a look. There it is, and you can see the base E model is definitely steeper than the base 2 model right there. Okay, very good. So yeah, this actually does bring up a good point. I had mentioned that it's used for all types of exponential models, growth and decay. So if it's a number bigger than 1, how in the world can we get it to be exponential decay? How does that fit? And well, let's take a look at example 2, and I think we'll answer that question. So it says use transformations here. I guess we only have to use a single transformation to sketch this. And if you think about y equals e to the x, and then y equals e to the opposite of x, or this negative x, well, what is that transformation? And again, we've been kind of working a lot with transformations over the course of the year. I hope you would all agree with me that this transformation is very simply a y-axis reflection. And so now, if you kind of think about how this would look, y equals e to the x, I'm just going to try to pinpoint it up here with my pen, would be this. Again, exponential growth, of course. Well, what happens when I reflect that over the y-axis? Well, everybody, that's when it becomes exponential decay. And so you end up getting something like this right here. So that's how we go with both exponential growth and decay for a singular base, in this case, base E. And let me bring that up on the calculator just to verify, of course, and then we'll just move forward on the next couple. I'm going to clear those out and just do e raised to the negative x, opposite of x, and graph, and there you can see, everyone. Nice looking exponential decay curve. Alrighty, let's do a couple applications with this. We talk a lot about population, dealing with exponential models. So as I mentioned, really, as we will see over the course of the unit, every exponential function can be written in base E. So I'm going to have one for India right here. And again, even before I read the problem, let's kind of box that one up. And then I'm also going to see one for China, 2 countries with the largest population in the world. So let's take a look at it. See if we can just get comfortable using the calculator here. And India is currently one of the world's fastest growing countries. The exponential growth model, and there it is, describes the population in billions 2 years after 2000. So I looked online and did a little research on their population, and during the 2000 census, this was the model that would this was the population in 2000, and then this would help with the exponential growth right here. And obviously, we're going to extrapolate using that piece. So it says, what was the population in 2000? I guess I kind of gave that away, but that's all right. I guess here's what we would do. If this is talking about a population model T years after 2000, then the year 2000 is year 0. I hope everybody is in agreement on that. Our model is starting at year 0, and that year 0 represents 2000. And so looks like I have this piece right here. Again, just kind of get comfortable with how this plays out. And times 0. I'll just kind of put it like that. And just like any other power, it looks like that exponent would be 0. So this times 0 is 0. E to the 0, everybody, of course, is 1. So this whole thing right here, this power would be 1. And 1 times this is just this right here. Now again, if I went a little too fast for you in that regard, do it on the calculator. And you would see that that would be the case. So this would be in billions, so just over 1 billion people in the year 2000. Make a prediction about India's population in 2040. Alrighty, so 2040, everybody. Again, I think we would use it as an input. That would be the population in year 40 on our model. And so let's go ahead and do this one, 1.014, again in billions, times E, and then raised to the 0.0158 times 40. Okay, so this one I'm not going to be able to do in my head, so let's pick up that calculator. And let's go on back. Alrighty, so I have 1.014, and then you could just do the E, so second, and then that ln button. We're going to see that ln in action in just a little while. So E, and notice it automatically knows. It knows you want to treat that as the base to a power, and so it gets you ready. In fact, it has the little caret right here. It has parentheses because chances are you're going to throw a couple things in there. So 0.0158 times 40. It knows the context for it, and so it sets you up very nicely there. And then let's see, it looks like about 1.908 billion based on what I see up there. So let's go ahead and put that in. I'll write exactly that piece, 1.908 billion in the year 2040 if the growth rate continues as it was projected in 2000. Okay, so let's see, we've done A, we've done B. Now part of the concern about India's fast-growing population is that eventually it could potentially meet and exceed the population of China. So China, currently the world's largest population. Let's see, I have a model for that as well. I looked online and again kind of used 2000 as a reference year. And this was the population in the year 2000. Again, you kind of see that in billions, 1.262 billion. Notice the growth rate is lower. So this number right here is a little slight variation on a growth rate. We'll definitely talk about this. You don't have to be too concerned about this piece right now. But basically, it's you can see it's a lower number than the one for India right up here. And so what would that look like if we model the two together? Would the population of India eventually catch the population of China? So let's see, it just says China's population can be modeled with that function. Same deal. Use a graphing calculator to determine when the populations of the two countries could be the same. Wonderful. Well, let's graph them on the calculator there. I'm going to get both these going. So I have in that first one, let me turn this. So I'm going to go on back in 1.014 and times E raised to the 0.0158x. So everyone, please type that in if you would. And then let's go ahead and type in population of China as well into the next one. And I think I saw it as 1.262. And then same deal, everyone, times E raised to the 0.009x. And so take a look at those two right there. Now what we're going to probably want to do is get a window that makes decent sense. We're in billions, so we don't have to go all the way up to a billion or 2 billion. It's already in billions. So I'm thinking just that we're going to go to our window here, and let's check it just over the 21st century. So I'm going to start at year 0. That would be 2000. And let's go to 2100 and just see what happens there. I don't know that that's ideal or not. Don't worry about the scale. And in terms of population, I don't know if we need to go all the way down to 0 there, but I'm going to anyway. And I'm hoping we don't get past the 2 mark there. We'll just see what happens. So up to 2 billion. If we need to modify that, we will. But I think that looks pretty good. I'm going to hit graph at this point in time. And let's see. Oh, nice. It actually worked. So let's go ahead and see what's going on here. Here's the population of India. Again, starts out lower, but it's growing faster. Here's the population of China, everybody. Starts out higher, but growing slower. And so you see at some point in time, the projection would be that the population of India meets and then exceeds the population of China. Let's go ahead and do an intersect. So everyone hit second, and then trace, and go to intersect. And remember, guys, just an enter, enter, enter should do the trick here. I'll do the same. And there we go. So it looks like projected, this is pretty interesting, that potentially in the year 2032, so basically this would be the 32nd year in the model, the populations would be the same, and we're looking at about 1.6, 1.7 billion people in each country. So let's see, let's go ahead and write that in, about 2032, give or take there. Okay. Good. So again, you can see today just working with E, nothing more, just seeing it in exponential models, but not too bad. Looks like those were exponential growth models, so I have a feeling I went with an exponential decay model for the next one, and it looks like I did. So here's what I have. Last example. The normal healing of wounds can be modeled by an exponential decay function. If A sub 0 represents the original area of the wound, then the area, A, so guys, this is going to be your dependent variable right here, the area of the wound after n days, so should have done this as t, but that's all right. So n days, so that's our independent variable, can be modeled by this function right here. So why don't we box that up? So notice it has that same look to it. It is slightly different, but we're going to have our initial value right in here. Then we're going to use our base E. Notice, everybody, this number right up here in front of the variable, it's negative. Do you remember one of the previous problems that we did during this lesson is by making that negative, it goes from exponential growth to exponential decay. So there's that nice piece. So that's how base E turns from growth to decay. And it says if healing is taking place, how long will the area of the wound be, or I'm sorry, how large will the area of the wound be after 3 days? Again, really not too bad. I guess we're going to use 1, just kind of starting it out there as a reference value for the initial wound. So that would be kind of like 100% of its area. I guess that's the idea for using 1. And so let's try this out. And so I'm going to put a 1 in there, and obviously don't have to write it in, but and then e raised to the negative 0.35 times 3. And again, you'll typically see it on the calculator kind of like that, so I'll put that in place as well. So I guess if you start out with the full area, that would be 100% of the area. After 3 days, what would be the area in relation to that? Okay, well let's grab the calculator and do it then. So I think the setup is okay. I gave you the model and I gave you the input, and any time I do that really shouldn't be too bad. But let's see, I'm looking at that 1 times, and then get used to that button right there, everybody. There's the e raised to button. And so e raised to the negative 0.35 times 3. Again, so take a look at that piece if you would. You can close it off. I don't think it's a necessity, excuse me. But in this case, I get about 0.3499. So, you know, really right in there. I'll write all those, just kind of struck me. If you want to write just 0.35, of course, that's fine. And so I guess just in terms of a relation or a percentage, if the original wound, starting at 100% of the area, after 3 days, again, that area of the wound starts to go down. It decreases exponentially. After 3 days, it looks like it's down to about 35% of the original area. Okay, great. So in this case, again, I've got a situation where, given the input, put it in, come up with the output, just using it now with this new base E. And then the last one here, it says use a graphing calculator to determine when the area will be 1/10 of the original area. So in this case, everybody, I'm giving you the output, and you're going to come up with the input. So this would be this piece right here. If we start with 1, well, 1/10 would be 0.1, of course. That would be the equation that I would solve. And again, we're getting a little closer to being able to solve that, but we're not there just yet. So that's why on your paper it does say use a graphing calculator. And we've done this before, and we'll do it again until we learn the algebra behind it. But basically, I'm going to put the model into the y equals, put it into the y1. I'm going to put the other one into the y2, so the other side of the equation. And then, of course, everybody, I'm going to see where they intersect. So again, we've kind of done this once or twice before, where you graph the first part, graph the second part, and see where they come together. And so I'll pick up the calculator and do that, but I hope everybody is at least in agreement on the setup here. Here's our model, and we want to see where that area gets down to 1/10. How many days? So what's the n value right there? Okay. Well, let's pick up the calculator and do exactly that. So to the y equals we go. Let's erase those. And so the first one will be the 1 times e raised to the negative 0.35x. Make sure you see that piece. And then the second one, everybody, will just be a 0.1. And again, what we have to do, the trick to this, I think, is just talking about the window. So I'm going to go to window up on the top of your calculator there. And let's kind of see what's going on. We're talking about x being the number of days. Well, you hope the wound doesn't fester too long there. So I'm going to go 10 days out. I don't know if that's great or not. We'll find out momentarily. And then let's see, on the y's, we'll go down to 0. And I think the max there, I think it started at 1 and it's decreasing. So I'm going to go from 0 to 1 and see what happens. Again, if you decide what different numbers work, that's fine. In some respect, it's very subjective. So I'm going to hit graph, and that looked pretty decent. You can see a nice looking exponential decay curve, everybody. And this is decreasing, decreasing, decreasing. At some point, it's going to be 1/10 of the original area. So let's go for it one more time. Second trace, intersect on that. And of course, everybody, enter, enter, enter. And we get about 6.58 days. That seems to be the case, and that looks perfect. Okay, so if you would, if you want to box that up, so be it, but I think that's definitely our final answer there. So again, just in conclusion with this, we're going to see all sorts of exponential models here. That y equals a times b to the x is certainly one way to model things that are growing or decaying exponentially. But there's going to be this other model here, this uniform base that we're going to be using as well. And we're going to see applications with that and really a context for why that plays out. So keep your eyes open for that. And please let me know if you have any questions on this lesson. And as always, I appreciate you listening, and good luck with some of the problems there.